Hey everyone, Mr. Skelton here. We are back at it for lesson 2 in unit 6. We're in our probability unit, and today we're going to be focused on the probability of multiple events. And we have 3 types of multiple events. One is independent, the second one is dependent, and the third one is mutually exclusive events. We're going to focus a lot on independent and mutually exclusive today. We're going to touch on dependent, but we're going to get to that in lesson 3 when we talk about conditional probability. So dependent and conditional probability sometimes can be one and the same, and so we'll talk more about that on a later lesson. So let's jump right into it. Our definition for the first type of multiple event is independent events, and you see this P, which stands for probability of events A and B taking place. That's kind of how you would read that out loud, the probability of A and B taking place. By definition, independent events are when the outcome of one event has no effect on the outcome of a second event. All right? Keyword there is does not. Keywords does not affect the outcome. So for an example, here's an example of an independent event. The probability of flipping a coin 3 separate times and getting a heads on 3 times in a row. So flipping a coin 3 times and you get what's the probability that you land on a head, and a head 3 straight times? Well, the flipping of a coin the first time has no bearing or effect on what the outcome of when you flip the coin the second time. It has no effect. So that's an example of an independent events. Now let's actually find this probability, right? So a coin has 2 sides, heads or tails. So on the first flip, we know that there are 2 possible outcomes, head or tail. We want a head, which would be 1/2. The second time we flip the coin is going to have the same fraction because there's still 2 outcomes on the second flip and we still want a head. On the third flip, there are still 2 outcomes. We still want a head. So we multiply those together and we get 1/8. Okay? When we're talking about independent events, we are going to multiply our fractions together or our situations together to get our final answer. Now, you can write your answer as a fraction. Sometimes you see that, or if you take your calculator out and go 1 divided by 8, you get 0.125. A lot of students like percentages, right? It's a little bit easier to kind of apply. So there's a 12.5% chance of you flipping a coin 3 separate times and it landing on a head all 3 times, 3 in a row. 12.5% chance of that happening, okay? Some students like visuals. I'll show you a quick tree diagram so you can kind of see this. If you flip on your first flip, you could get a head or a tail. On the second flip, you could get a head or a tail. Head or a tail. On your third flip, you could get a head or a tail. On this one, it could be head or tail, and head or tail. And so this tree diagram, that's your first flip, second flip, third flip. You don't have to write this down, but you can see after that third flip how many options are there. 1, 2, 3, 4, 5, 6, 7, 8. And how many times did you get heads 3 times in a row? Just once right there. That's the only time where 3 straight heads showed up out of 8 opportunities. So that's kind of a visual for you. This is the formula, and again, I kind of mentioned this already. Sometimes in textbooks or in future classes, you may see something written like this: the probability of A intersection B. Okay, you could see that notation. That's just a different way of writing it. It's called notation, and we sometimes refer to that as the AND symbol. Okay. So that's independent events. Does not have effect. Flip it. Let's go to the next one here. So dependent events is a little different. It's when the outcome of one event actually affects the outcome of a second event. All right. So here's an example right here of dependent events. Find the probability of guessing the outcome correctly in a raffle drawing where first, second, and third place prizes are selected at random from the same pool of 10 people where you can only win 1 prize. Okay, so let's try to make sense of this. So out of 10 people, we're going to do a raffle drawing for the first place. What would that probability be? 1 out of 10, right? There's 1 person out of those 10 who's going to win first place. However, since you can only win 1 prize once this person, Tom, Tom won, he won first place. Well, Tom is not eligible for second place. So what is the fraction then that represents the probability for that second place? Well, that would be 1 out of 9, right? Because Tom no longer exists in the pool for the second place prize. And then likewise for third place, so let's say Tom, and then Judy won second place. So Tom and Judy are out of the mix for third place, so the probability of third place would now be down to 8 participants. That is an example of dependent events because the outcome of the first event affects the second, and the second affects the third, so on and so forth. Okay. Now we're still timesing these fractions together. I'll save you the drama. It's 1 out of 720. As a decimal, that is 0.00138. So if you move the decimal place over twice, 0.138% chance of someone picking those 3 people at random, Tom, Judy, and Sally. There's a 0.138% chance that they picked that correctly. That's the probability of guessing the outcome correctly. So very slim, to say the least, but that's dependent. Okay. And we'll touch more on this probably lesson 3 is when we'll dig into a little bit of that. But for your assignment and for quizzes and tests, you need to know the difference between dependent and independent events, definition, and examples. You'll have to be able to identify outcomes that either affect or don't affect each other. Okay, so let's try one on your own. Go ahead and pause real quick and give us one a try and see what you come up with. All right, so you can read the situation here. At a picnic, there are 6 bags of fat-free chips and 8 bags of regular chips. There are also 10 cans of diet soda, 12 cans of regular soda. You grab a bag of chips and a can of soda without looking. What is the probability you grabbed a bag of fat-free chips and a diet soda? So, first of all, independent or dependent? Well, this is going to be independent, right? Nothing about me grabbing chips is going to affect the soda. So let's just take a look at then the probabilities for each. Let's take a look at the fat-free bag of chips. Well, we know that there are 6 bags of fat-free chips, so that's what we want to have happen. Out of the total amount of bags of chips that are possible, 6 plus 8 gives you 14. We want 6 of the fat-free, there's 14 total, okay? And we're going to times that by diet soda. Again, me grabbing a bag of chips has no effect on the outcome of me grabbing a soda. So we want diet soda. I believe there were 10 cans of diet soda, and there were 22 total. So we're going to multiply those 2 together. If you do that, you get 60 over 308. Okay, if you're going to leave it as a fraction, I can show you if you don't know this already on your scientific, you can use your fraction button, right? You can go 60, fraction button's right here, just hit that over 308, hit equals, and it reduces the fraction for you. So you get 15 over 77. That would be our final answer. If you actually want to find the decimal version of that to make it a percentage, oops, bear with me here, you get 0.194, so basically 19.4% chance. There's a 19.4% chance that you grabbed a bag of fat-free chips and a diet soda. Okay, again, that's independent. Okay, now we're going to get into mutually exclusive. So there's two slides here. The top one, I think you'll be able to make sense of fairly easily, and then the second one sometimes can be a little tricky. So let's go through this. You'll notice right away it says or. Okay, so it's not and, so it's or. It's a little different. Mutually exclusive by definition, and again, this is the third one. So we have independent, dependent, and we have mutually exclusive. Mutually exclusive events are 2 events that cannot happen at the same time. For example, rolling one die, and getting a 2 and a 6. That is impossible. That is just impossible. You can't roll a single die and it show up a 2 and a 6. Now, what can happen is you could get a 2 or a 6, and that's kind of the road we're traveling down. So, for example, let's just change this and say, what is the probability that you roll one die and you get a 2 or you get a 6? Okay, well, we know that there are 6 total numbers, so you'd have a 1 in 6 chance of getting a 2, and you'd have a 1 in 6 chance of getting a 6. We're going to add those together. Whenever you see or, you're going to add. What's the probability of rolling a 2 or the probability of rolling a 6? Not and, so we're not timesing them together, we'd be adding them together. So we get 2 over 6. Remember when we add fractions, common denominator, we'd get 1/3. So you basically have a 33.3% chance of that happening. Here's another example right here, example 4. It says, suppose students at HHS Homestead can only take one foreign language, and 42% of the students take Spanish, while only 16% of the students take German. What is the probability that a student chosen at random takes Spanish or German? So this is, you can't take both, right? You can only take one. You can only take one, so you couldn't have an and here. What's the probability to take Spanish and German? Can't happen. That's an example of mutually exclusive. You can only take one. Well, this is a kind of a different example than the one we just did here in the sense that they're percentages and not fractions. This was an example with one with fractions. So here it's pretty basic. You just have 42%, you can make it a decimal, 0.42 plus 0.16, and add those together and you should get 0.58, which is 58%. So the probability that a student chosen at random takes Spanish or German, it's 58%. All right? And here is your formula. So we talked about formulas on that first independent one. Again, if you have an or, you're going to be adding them together. Okay? This is the one that's kind of tricky. Non-mutually exclusive events. So what this basically means is there's going to be something that takes place in the question where you have overlapping of the events, and I'll kind of explain what that means. So here's an example of non-mutually exclusive events. And again, you'll still see it's still an or. The formula you can already see is present, which is right here. So you can see what's already going to be different, which is this right here. And so let's take a look. What's the probability of drawing a card from a deck of cards and getting a queen or a heart? A queen or a heart. Well, we see the word or, okay? What's the probability of drawing a queen? Well, if you know anything about a deck of cards, there's going to be 4 queens in there out of 52. There's 52 total cards. If you don't know cards, there's 52 total. Shouldn't assume anything, right? We're going to add queen or a heart. Well, there's 13 hearts in a deck out of 52. However, there's one situation within this where there is overlapping, right? We have 4 total cards. Let's say this circle, I'm going to make a Venn diagram real quick. That's the queens, there's 4 of them, okay? Here are the hearts, we know there's 13 of those. Well, there's a queen of hearts, right? There's one card that is a queen and a heart, and that's the queen of hearts. And so if there's one here, then that means this number is 3 because 3 plus 1 makes 4. If there's one here that they share, okay, queen of hearts, that means there's 12 here. That's a Venn diagram, and you're going to see how this kind of works. If we just add these together, my final answer would be 27 over 52. That's going to be incorrect. Why? Because we want to subtract that one situation that overlaps. So really what we would have is 4 over 52 plus 13 over 52, subtract 1 over 52, and that 1 represents that queen of hearts. And so our final answer then, would be 26, it'd be 16, right? It'd be 16 out of 52, okay? And that would be my answer. 3 plus 1 is 4, 4 plus 12 is 16. And so you can use a Venn diagram to get your answer. You can use the formula to get your answer. Either way works. You just have to think about which situation represents something there where there's something that overlaps, okay? Let's see if anything else I wanted to show you. Again, that's just not, if A and B are not mutually exclusive, just make sure you subtract where they overlap, and we should be in good shape. All right, let's flip it over, and we're almost done here. This question actually was, I wrote it wrong, so let me fix this real quick. The question at the bottom should say, what is the probability that a student in the survey played, shouldn't say either, or it should say either, played either basketball or soccer. That's what I wanted it to say, okay? So hit pause, try this one, see what you can come up with. All right, in the situation we have 50 freshmen, we want to figure out what's the probability of basketball or the probability of soccer. So or means we're going to be doing mutually exclusive events. Now, do we have anything that overlaps here? You'll read we have 24 people who played soccer, 29 people who played basketball, 13 that played both, okay? So there's a group of students that overlapped, and then 10 people who didn't play anything. And so what we want to do is figure out what's the probability of people who played basketball. That'd be the 29 over 50, because there's 50 total students, plus the amount of students who played soccer, which which was 24 over 50. And then what do we want to subtract from that? Well, we want to subtract the 13 people who played both sports. And so if we do that, we should get, I believe, it's 40 over 50. 29 and 24 minus 13, I believe, is 40. And so 40 over 50, or 4/5, would be our answer if you wanted to make that a decimal, which is a little bit easier on the eyes, right? And easy, 4/5, a little bit easier to associate things with. 80% chance. There's an 80% chance that a student in this survey played either basketball or soccer. Okay. The Venn diagram here, again, not going too crazy into the detail of it, but again, there's the 13 people who played both, because remember, this is the intersection of both, where people played soccer and basketball. 13 plus 11 gives you the 24 for the soccer. 13 plus the 16 gives you the 29. And again, you could just add these up, 11 plus 13 plus 16, and you'll still get the 40. Okay? All right, y'all. Well, I hope this went well for you. I'm sure you'll have a couple questions, and that's totally normal. Hopefully we can clear up any loose ends in class, and I look forward to seeing you in class. Take care.